Okay, so this is the final video in our Applications of Differentiation chapter, and to be honest, it is a slightly obscure collection of things here. I've called it families of functions that corresponds with a particular exercise in the textbook, but really this is a place where they've included a series of questions which they weren't sure where else to put them. But the idea is that what we're looking at here is sort of generic functions. So if, for example, if you look at example 1 here, we have a cubic function, but it's not a specific cubic x minus 5 squared times x minus 3. It is the generic family of cubics that are x minus a number all squared times x minus a number. Okay, and so we want to think more generally about the features of this function rather than a specific case of this function. And all the same techniques we know around derivative and calculus obviously apply. So there's going to be a little bit more algebra here. I'm going to do all of that algebra by hand, but I'll also just have a look at how you would solve these problems with the use of your CAS as well. But there's some nice algebra here that's worth you practicing. Okay, so let's just work our way through a couple of examples. I think we'll do 3 examples in total here. So the first example, we're looking at this function. Okay, so as I said, it's a generic cubic function, x minus a number all squared times x minus a number. A and b are both positive constants, and b is bigger than a. Sketch the graph of y equals f of x. Okay, so immediately a cubic of this form, we can tell it has x-intercepts when x equals a and when x equals b. And we know both a and b are positive and b is bigger than a. So we can plot a and b, sorry, I'm just going to get that slightly straighter. We can plot a and b on our axis. You can put them wherever you want. They need to be to the right of the y-axis, and a has to be smaller than b. Okay. We also know it's a positive cubic. If we were to expand it out, it'd be positive x cubed. And we also know that at x equals a, we get a turning point, whereas at x equals b, the graph will cut through the axis. And so we know we're going to have a cubic that turns here at this turning point and then cuts here through that turning point. Right, let's calculate the y-intercept there. So f of 0 equals a squared, sorry, it's negative a squared, but that is the same as a squared, times negative b. So we're just going to have, that's positive a squared times negative b, and so we get negative a squared b. So the y-intercept is at 0, negative a squared b. Now, for now, I'm going to ignore that other turning point because actually the next questions walk you through finding the coordinates of that turning point. So actually this question at part A should really say, sketch the graph of y equals f of x, marking all axis intercepts, and sort of clarify that you don't actually need to mark the coordinates of the other turning point. Because as I said, parts B and C are going to walk us through actually finding the coordinates of that point. Okay, so find the derivative of f of x with respect to x. Alright, so f of x is x minus a all squared times x minus b. So we could expand all that out to differentiate it, but given that it's going to have a lot of letters flying around, I'm going to choose to use the product rule here instead and leave it in its current form. So differentiating x minus a all squared is 2 times x minus a to the power of 1, and then times the derivative of x minus a, which is just 1, and then we're leaving x minus b, and then plus, we'll leave x minus a all squared, and derivative of x minus b is just 1. Alright, so what have we got here? We've got 2 times x minus a times x minus b, take away x minus a all squared. Nothing wrong with that in terms of the answer for this particular question, but it's going to be much easier in the next question if we focus on factorising this. So I'm going to identify that I've got a common factor of x minus a, and when I take that out, in the first term there I'm left with 2 times x minus b, and in the second term I'm left with another x minus a. So we can focus on tidying up that second bracket. So we get 2x minus 2b minus x and plus a. So we actually have, oh sorry, I don't know, I've added a minus in there where there shouldn't be. My apologies. Can we just correct? So there's a plus there, this should still be a plus here, this should still be a plus here, and so therefore, sorry, this is plus a, plus x, sorry, and minus a. Sorry for that. Okay, so we're going to have x minus a in that first bracket, 2x plus x, so 3x, minus a and minus 2b. Okay, as I said, in terms of having answered this question, we could have stopped up here, but having factorised it fully is going to be helpful in the next part, and you would just need to do that factorisation in the next part anyway. Okay, so the next part is to find the coordinates of the stationary points. So that's going to be about solving our derivative equal to 0. So now that we've factorised our derivative, so it's up here, x minus a times 3x minus a minus 2b, I think it was, yep. Okay, so we would need to get to this point to do this solving. We've got null factor law here, two things multiplying together to equal 0, so that means either x minus a equals 0, which means x equals a, which we actually already knew. We know there's a stationary point when x equals a from our sketch. Okay, we've already drawn that. And then the other one will be from this solution, so 3x minus a minus 2b equals 0. So that is 3x equals a plus 2b, and so x equals a plus 2b over 3. Alright, we already know, so we want coordinates of the stationary point, so we found the x coordinates. We know when x equals a, y equals 0, we've already got that on our graph. So we know we have a stationary point at a0, and then obviously we're going to need to substitute a plus 2b into our function to find the y value of this other turning. Sorry, a plus 2b over 3 into our function to find the turning point of this other, to find the y coordinate of this other turning point. Okay, so I'm going to put that into the function. I'm going to go, so the function, remember, was, let's go right back up to the top again. Function was x minus a all squared times x minus b. So x, which is this, minus a all squared times x, which is this, minus b. Okay, so again, I'm going to run through this question again using your CAS, but this is all algebra that you should be able to do, and I would encourage you to sort of get that practice where you get the opportunity to. Alright, so common denominator in the first bracket here is going to mean we get minus 3a on 3. So a plus 2b minus 3a, so that's going to be 2b minus 2a over 3. That's just getting a common denominator in that first bracket. And then common denominator here, again, we're subtracting 3b on 3, so a plus 2b minus 3b, so that's a minus b over 3. Okay, again, a few things. There's a common factor in that numerator there. We've got, and in fact, I'm going to take out negative 2, just so that I get this looking at the 2 fractions. So if I look at this first, I'm going to write this as negative 2 times a minus b, because I've also got the a minus b in the second fraction, and therefore that's going to collect together really nicely. So in the first fraction, if we now square everything, negative 2 all squared is 4. A minus b all squared, I'm not going to expand it out because it's actually going to be nice and neat how it is. It's over 9, and then we've got a minus b over 3. So now multiplying those together, we have 4 times a minus b cubed over 27. Okay, so therefore the coordinates of the other point are a plus 2b over 3 and a times a, sorry, not a, 4 times a minus b cubed over 27. Okay, so there's our 2 stationary points. So that ugly stationary point we've just found there, that is this second point down here. Okay, so Part D, find the values of A and B if the stationary points occur when x equals 3 and x equals 4. Okay, so thinking about our graph, we know that the first stationary point is the one at A0. So if we've got stationary points when x equals 3, this one has to be 3 and this one has to be 4. Okay, and so therefore we know A equals 3 and the x coordinate of that other ugly stationary point will equal 4. Oh, sorry. And so we can use that information. So immediately we know that A will equal 3, and we know the x coordinate of the other stationary point, A plus 2b on 3, will be equal to 4. Alright, so we can sub A equals 3 into this, so this is 3 plus 2b on 3 equals 4, so that is 3 plus 2b equals 12. 2b equals 9, and so b equals 9 over 2. So find the values of a and b. A is 3 and b is 9 on 2. Again, let's just quickly run through that with your CAS. So if you were presented with this question and you had your CAS, the first thing I would be doing would be to define f of x is x minus a, all squared. Now this is a good thing too. You've noticed that that a has come up as bold, and that's because in a previous example, in the last section when I did the max-min problems, I defined a function called a of t, I think it was from memory. So this is going to cause problems here. Now you could obviously just change a in the question, but actually longer term it would be better to delete a. So I'm going to go just tidy things up here. Menu 1, 4, clear a to z, and clear all my previously defined functions if they're called a, b, c, d, e, f, g. It won't clear every function, so if I now press the variable button, so the button above the 9, it lists that I've still got two functions defined, dA and dV, and that's because they are not a to z, okay? They are not a of something, b of something, c of something, d of something, because I combined two letters, so they're still there. Now, realistically, that's not going to cause me any problems. If I, at some point later down the track, define a new function as dA, it'll just override that. I'm unlikely to have dA appearing in an equation and therefore causing any problems. If you do want to delete them though, you can go menu 1, delete variable, number 3, press your variable button and choose that's the variable I want to delete. Now I need to give it, I don't remember what it was in terms of, t maybe? Yeah, so I'm in a bit of trouble here just guessing. So it really doesn't matter, and it wouldn't normally matter. I would very rarely delete, f of x I define repeatedly. I wouldn't delete them. You just keep overriding it, so it won't matter. Okay, let's go back to here. I'm just going to clear my screen and get rid of those. Okay, let's go back here. Let's define our function, menu 1, f of x is equal to x minus a. Now a doesn't come up as bold, squared, because I've deleted that definition, x minus b. Okay, we've defined our function. Sketching the graph, you couldn't get your CAS to sketch the graph unless you substituted values for a and b. It's easier and quicker to do that by hand anyway. Part B though, finding the derivative, shift minus derivative with respect to x of f of x is that. Okay, so again it gives you that nice factorized form, which is helpful. The next part, which is finding the coordinates of the stationary points, so you would now be solving your derivative equal to 0 for x. So there's your x coordinates of your stationary points, and then obviously you need your y coordinates, so f of a, subbing a back into your function, is 0, there's your a0, and f of a plus 2b over 3. Gives us what we found by hand. Now just quickly, in making that second substitution, I typed out a plus 2b divided by 3. You can make use of your answer above, so you don't have to retype it. So I could scroll up here, but it is a little bit fiddly given that it's stuck in that sort of larger definition with two x values. If you press the right arrow to move your cursor to the end of the line, and then scroll across, and if you hold down the shift key while you scroll across, shift and scroll, it'll highlight just a section, and then you can press Control C to copy that, and you can scroll down here to Control V paste in the function. So obviously if that was a much uglier expression than that, it might have been worth doing that. However, I made the assessment in the moment that I could type it out quicker than I could muck around with copying it. And those are the sorts of things that you need to start using your CAS a lot to be able to make those decisions. I know I could do it this way with my CAS, but it's quicker to do it this way. I know my CAS can do this, but it's quicker to do it by hand. Okay, so we found the stationary points, and then the second part, really is very quick by hand. I wouldn't bother with my CAS for part D. Okay, let's have a look at another example here. Example 2, so this time we're considering a function of the form g of x equals x cubed minus ax. So again, a family of cubic functions, but different kinds of equations here. we want to determine the intervals on which g is a strictly decreasing function and the intervals on which g is a strictly increasing function. So we have to recall our definitions about strictly increasing and decreasing, which are really just about including the endpoints. Strictly increasing, positive gradient, but include the endpoints, and same with decreasing. So we really want to think about what this graph looks like though. So let's have a little think about our function. So g of x is x cubed minus ax. So I might start factorising it. This common factor of x is with x squared minus a. And then I could probably factorise by thinking about a difference of two squares. So that's x minus root a and x plus root a. So that allows me to think about this as a cubic with 3 x-intercepts. Each of those are linear factors, so the graph cuts the axis at each of those points. It is a positive cubic, so it goes up as we travel from left to right. And so we essentially have something like this. So that is square root of a, this is negative square root of a, and obviously 0, positive cubic. So we're going to need to think about the turning points. Okay, so we want to look at the derivative. Much easier to differentiate the expanded form, not the factorised form. So I'm going back to the original there. Derivative of x cubed is 3x squared. Derivative of ax is just a. And making that equal to 0 for my stationary points. 3x squared equals a. X squared is a on 3. And so x is plus or minus square root of a on 3. Alright, so now again, think about we actually don't need the coordinates of the stationary point here because we're determining the intervals or the x values over which g is strictly increasing or decreasing. So we actually don't need the y values, so we won't bother finding them. So that point there is negative square root of a on 3, and that point there is positive square root of a on 3. Okay, and so therefore we can think about, strictly decreasing. Decreasing 4. So we're looking for where we have negative gradient. Okay, so that's certainly happening in here. But remember, strictly decreasing, we can include the endpoints because the definition is about any point on the right will be lower down than the point on the left, which would be true including those endpoints. So strictly decreasing for x is an element of square bracket, negative square root of a on 3 to positive square root of a on 3 square bracket. And then we are strictly increasing 4. So again, we're looking for where we have positive gradient. So that's going to be here, including at that point. We don't have positive gradient at that point, but the function is strictly increasing over the interval from negative infinity up to and including that point. And again, strictly increasing out here. Okay, so we are looking at x is an element of negative infinity up to negative square root of a on 3, inclusive, and inclusive of a square root of a on 3 up to infinity. Okay, again, we could define our function, use our CAS to find those x values of the turning points. The CAS would write those points differently because it would rationalise that denominator of root 3, but same values ultimately. Find the equation of the tangent to the graph at x equals negative a. Okay, so at x equals negative a, we want the tangent. So again, let's do this by hand. We can have a look at how we can get our CAS to help us as well. So equation of the tangent means we need the gradient at that point, and we're also going to need the y value at that point. Okay, so we want g at negative a. So our function, is x cubed minus ax. So that is negative a cubed minus a times negative a. So that is negative a cubed plus a. Okay, and so this means we have the point. That's just giving me the y coordinate of the point. I've just subbed into the original function. I might write that as a minus a cubed just to be a bit neater. Alright, so that's my point, and then we need the gradient at negative a, so g dash at negative a. We've already calculated g dash x up here. So let's sub into that, 3 times negative a squared and minus a. So the gradient is 3a squared minus a. So this tells us that the gradient of our tangent is 3a squared minus a. So Sorry, that A is a bit illegible. Okay, so we've got gradient and a point. So y minus y1 equals gradient times x minus x1. So y minus the y coordinate of our point, a minus a cubed, equals the gradient, which is 3a squared minus a, times x minus the x coordinate, so x minus minus a, so that's x plus a. Alright, let's just tidy this up to make y the subject. So we're actually going to have y minus a plus a cubed equals, I'm not going to expand out the gradient because I still want to be able to have something times x. So 3a minus a all times x, we're going to leave that like that, plus we're going to have a times 3a squared minus a. Alright, so y is 3a squared minus ax plus, that is 3a cubed minus a squared, and now I'm moving the terms from the left hand side to the right hand side, so we're going to have, we're going to have plus a and, oh sorry, I've lost an a there, haven't I? Okay, I've realised where I've made an error up here. My apologies, hopefully you picked it up as I went. So this minus a times minus a, that should be a squared, and so the y coordinate is a squared minus a cubed. So we get a squared minus a cubed here, a squared minus a cubed here, and so I'm adding a squared. And then I also have to subtract a cubed. Okay, so let's just tidy up those like terms there. So it's y equals 3a squared minus ax, and then we've got 3a cubed minus a cubed, so that's plus 2a cubed, and we've got minus a squared plus a squared, so they cancel out. And so there is our equation of the tangent. Sorry. Okay, again, let's quickly just run through how the CAS would help us here. So we are looking at defining our function, defining g of x equals x cubed minus ax. Now be careful with definitions like this, you need to make sure that you type a times x, otherwise it doesn't read it as a product, it just reads it as one variable called x. So defining your function, derivative of your function, so derivative of g of x is exactly what we found by hand, solving our derivative equal to 0 for x is also similar to what we got by hand, although as I said with the rational denominator. So they've written it as square root of 3a over 3, which is the same thing. So this is the same as plus minus square root of 3a all over 3. You can use that instead in your answers. Okay, and then from there you can interpret your strictly increasing, strictly decreasing in part A. And then in part B you're finding the equation of a tangent. So remember, if this was a question with a CAS, this would be worth 1 mark, and so you wouldn't be doing all of this by hand. As I said to you in the tangents and normals video, this is the one thing that people tend to forget. I find students forget that their CAS can find an equation of a tangent very easily. So menu 4 for calculus, 9 for tangent line. You want the tangent to g of x, comma, when x equals negative a. And there's our equation. So let's have a look at how that compares. Okay, so they've factorised this as a times 3a minus 1. But otherwise it's exactly the same. Alright, good. Let's have a look at our third and final example for this video. A cubic function has rule h of x equals, so the most generic cubic, ax cubed plus bx squared plus cx plus d. It has an x-intercept when x equals 3, passes through the point 1, 2 with a gradient of 35 at that point, and has a turning point at x equals 0. We're going to use our CAS here because we're essentially going to end up with 4 simultaneous equations with 4 unknowns. But let's be clear about what the information is that's going to enable us to create those simultaneous equations. So we've got our function definition, h of x equals, it has an x-intercept when x equals 3. So x-intercept when x equals 3, that means that it goes through the point 3, 0. Okay, so therefore h of 3 is equal to 0 will give us our first equation. Passes through the point 1, 2. Okay, so again, h of 1 equals 2. It has a gradient of 35 at that point. So h dash of 1 at x equals 1, the gradient is 35. and it has a turning point at x equals 0. Okay, so again, derivative at x equals 0 is equal to 0. Okay, so there's my 4 simultaneous equations. We've looked at entering this kind of thing into your CAS before, and this is an example where I would say that it is strongly advisable to define your derivative function, because you'll remember we talked about previously that if you're going to enter something like this into your CAS, you can't just remembering that your CAS is going to find the derivative by doing d dx of h of x. Okay, and you can't just do d dx of h of 1 because h of 1 is a number, and when you differentiate it you'll get 0. So you need to do derivative of h of x given that x equals 1, so that's subbing 1 into your derivative, and then you need that whole thing to equal 35. And you have this problem here with this equal to, equal 1, equal 35, so there has to be a bracket in there, which means you need a bracket here. Okay, and if you don't type this bracket in first, you're going to have real trouble putting it in later. So you can enter that in, but actually it might be easier if in your CAS you define a separate function as your derivative. Okay, so we'll have a look at that. Just going to erase that for now. So let's go to our CAS. We're going to need to first of all define the original function. So menu 1,1, h of x. Oops, sorry. So h of x equals, again being careful about the multiplication here, implied multiplication, so it's a times x cubed. You need to explicitly write that multiplication, plus b times x squared, plus c times x, and plus d. Okay, so there's my general cubic, and then we want to set up our simultaneous equations. Now, I'm going to do it the way I showed you before. So menu 371 for simultaneous equations. We're going to have 4 equations, and the unknowns are going to be a, b, c, and d. And so my first 2 equations are very easy to enter into the CAS. Literally, h of 3 equals 0, h of 1 equals 2. Okay, now when we need to put in one involving the derivative, remember you must type the bracket first or you'll have difficulty later. Shift minus for your derivative, derivative with respect to x of h of x, outside of the derivative bracket, given that x equals 1, and then outside of that bracket we want the whole thing to be equal to 35. And then we need to repeat that for the other one. So put your bracket in first, shift minus, derivative with respect to x of h of x. Now again, you could scroll up and do some copying and pasting and edit it, but it's a bit fiddly in here, so ultimately it ends up being quicker typing it out, but it is still quite a fiddly entry. This time it's when x equals 0, and then the whole thing is equal to 0. Alright, and so we get our values for a, b, c, and d. Alright, so this gives us a equals negative 71 on 7, b equals 229 on 7, c equals 0, and d equals negative 144 on 7. Find the values for a, b, c, and d, so we've done that. Okay, if it asks you to give the equation, then you would write those values out in the original function. Let's just be clear about if instead of typing in this really complicated entry, if instead I defined a separate function for the derivative. So if we define, menu 1,1, define derivative of h, I'm going to call it dh of x, as being equal to literally the derivative of h, then it makes the entry of the simultaneous equations quicker, because now it's menu 371, 4 equations, your unknowns are still a, b, c, and d. Subbing in the points, so h of 3 equals 0, h of 1 equals 2, but now the derivatives don't require that complicated entry because we can just use the fact that dh is the derivative of h according to my definition, so dh of 1 equals 35, and dh of 0 equals 0. So it's worth, in this instance, creating your derivative function so that the substitution in the simultaneous equations is much, much easier. Okay, part B is find the equation of the image of h of x after it's translated by this matrix translation. So this is right 5 and this is down 9. Okay, so we're going to need h of x before we can do that. So I may as well write that out up here. So h of x is going to be negative 71 on 7x cubed plus 229 on 7x squared plus 0x minus 144 on 7. You might also choose to factor out that 1/7 or even negative 1/7 because it is a nice common denominator, and just then have 71x cubed minus 229x squared plus 144. You could just factor out positive 1/7 if you prefer. Okay. Either way, h of x. So if we want to find the equation of the image of h of x after translation to the right by 5 and down 9, what we want here is h of x minus 5 is right 5 and down 9 is take away 9. So again, let's have a think about how our CAS can help us with this. So the first thing I need to actually do is, I've already got h of x defined, but I now want to actually put my values for a, b, c and d into h of x. The easiest way for me to do that is h of x, given that, scroll up and press enter to copy that. So I'm now doing h of x given that a is this, b is this, c is this and d is this. So that's now worked out h of x. There's h of x. It's now defined h of x with the numbers in it. That's what I've written out in part A. Now that makes it very easy for me to do. So again, let me just verify that. If I type h of x now, sorry, so it hasn't actually defined it. So now I'm going to redefine it. So now I'm going to go menu 1, and I'm going to redefine h of x as being equal to this. Okay, so h of x given that, and just copy down your answer line to sub the numbers in, and then now define that as being h of x, which now makes it very easy to work out what h of x minus 5 minus 9 is. My CAS will do all the grunt work for me, and it is, again, let's factor out that negative 1/7 or positive 1/7, that's up to you, just so I don't have to write out so many fractions. So this will be 71x cubed minus 1294x squared plus 7615x and minus 14393. So it's ugly, but it's very easy to get to that answer by utilising your CAS effectively and efficiently. Okay, exercise 10G, as I said, a slightly strange collection of questions, but this idea of a sort of generic function, whether it be, these examples were all cubics, but obviously there could be other functions as well, and then thinking about working with those functions, including finding derivatives and stationary points, etc., etc.